Is my screen visible to you?
Yeah.
Yes, sir.
Okay, okay, okay. Okay, good morning and welcome back for the day two session on week two. Today I will be talking about GPUs, mainly the introduction to GPUs and CUDA programming, optimizations, and some of the research directions. So as you know, I'm an assistant professor and I am also one of the organizing members. Okay, so this is a brief outline of my talk. So I'll briefly introduce the topic, motivate the topic, and then I will give a brief introduction to GPU architecture, and then how to write programs on GPUs using CUDA programming language. And then I'll show you how the instruction gets executed when you write a program on the GPU. And then I'll talk about some of the GPU specific optimizations and some of the research directions. So this just gives you some overview about GPUs and what are things are happening and how to write the programs, etc. Okay, so for many decades, the single core processors were very popular by exploiting the instruction level parallelism and core clock frequency and Moore's law. You are able to put more resources. But around mid to late 1990s, because of power wall, we had several power constraints and heat dissipation, etc. So from then onwards, multi-core processors and accelerators like GPUs have started evolving it. So then you may be asking a question like why GPUs? So we have already multi-core processors, right? So the multi-core processors are good at task level parallelism. So you have independent cores, and then the cores can perform different tasks also. But there were at times where you were actually need to process the graphics application, so and you wanted to run them very quickly, and that was getting computationally expensive around those days. But the problem was the key operation that graphics application that they try to do is that you want to perform same operations on multiple data elements. So this was not very efficient when you try to do it on multi-core processors. So people have come up with the efficient paradigm, that is SIMD execution pattern, where you are trying to execute a lot of the same operations on multiple data at once. So this has led to the motivation of design of graphics processing units. So the early version of the graphics processing units are basically specialized for graphics application only, and they exhibit SIMD execution that we talked about in the last week. The early versions of GPUs were less programmable, and the first GPU was launched with NVIDIA GeForce 256. But after several years, in 2007, the fully programmable GPUs were released. So, like NVIDIA has also launched a programming paradigm called CUDA, so it allows the general purpose users to write programs on the GPUs. So now we have general purpose GPUs devices also. So let's try to understand how the GPUs differs from the single core CPU and multi-core CPUs, and in terms of the computer architectures. So you know the traditional CPU, single core CPUs, processors. You have a processing cores, and then you have multiple levels of caches, and then you have a DRAM hierarchy. And in case of multi-core processors, what you have is that you have set of processing cores. The processing cores are typically fewer in numbers, maybe an order of tens, or maybe less than 100 itself. So you have each processing core is associated with L1 cache, or you could also have L2 cache. Then you also have a common cache, which is the next level of cache, and then you have DRAM. This DRAM and the last level cache can be accessed by any of the processing cores. Now, the main thing over here is that different processing cores. So you have 4 cores here. So our core can perform different tasks. So let's say if core 1 is performing addition, core 2 can perform multiplication, and so on and so forth. Core 3 and core 4 can perform different operations. But now let's try to see how the GPU looks like now. GPU contains several thousands of processors. So here in multi-core CPUs, you only have few processors, but in GPUs, you have thousands of processors. And these thousands of processors are grouped into what is known as streaming multiprocessors. So with streaming multiprocessor, now you have certain, these are grouped depending on the number of streaming multiprocessors. And these streaming multiprocessors called as SMs. So within each SM, you also have registers, and you also have scratchpad memory or shared memory, which can be accessed by one of the all the processing cores. And you also have L1 cache, and there is also L2 cache and global memory, which can be accessed by any of the common any of the processing cores. Now, the main the difference between the execution pattern from the GPU versus CPU is that several processing cores within a streaming multiprocessor basically execute the same instruction on multiple data. So if one is performing addition, then some of the other cores will also perform the same addition, but on different data elements. But that's not the case in case of multi-core processors. Now, because you are able to perform the same operation, you are able to require less resources, and then you are able to achieve high throughput. And this has started the evolution of GPU processors. So this is actually one of the recent GPUs. So it's called a GV100, Volta V100 architectures. So this is a picture I've taken from the white paper of NVIDIA. So you can see that there are so many green boxes here. So I have one highlighted in the yellow box. This is basically one streaming multiprocessors. Now within this streaming multiprocessor, there are again several hundreds of cores. And like this, you can see so many streaming multiprocessors are there. And you also have an L2 cache, which is common to all of these. Okay, if you look at briefly about the specifications, how actually the GPUs are evolving. So here I'm showing you four GPUs. So the K40 is the Kepler architecture, and M40 is basically Maxwell architecture, P100 is Pascal architecture, and V100 is one of the Volta architecture. Nowadays we have Turing and then Ampere architectures as well. So let's try to look at how the SMs are actually increasing. So the number of SMs are 15, 24, and 56 and 80. So the number of SMs are increasing, and number of processing core also within each SM are also increasing. So you can see that. So each SM, each GPU has 2880 in K40, so on and so forth. Now V100 has 5120. Now the latest architecture Ampere has around 10,000 processing cores. So you can see that it offers multiple processing cores and around thousands of processors. And but the main difference in the operation is multiple processing cores will execute the same operation on multiple data elements. And if you just try to look at how CPUs are actually in terms of performance, in terms of bandwidth, how different they're different from GPUs. So GPUs and CPUs are different. So you can see this graph. Basically here x-axis on the left hand side, I'm showing you the memory bandwidth. On the right hand side, I'm showing you the performance in terms of giga floating point operation per second. So over the years, you can see that from 2016 to 2022, the GPU performance actually the GPU memory bandwidth is increasing, but GPUs has been increasing very significantly. And in terms of performance, also GPUs are able to deliver high throughput because they are able to uh, pack more and more processing cores in a single GPU itself, and people are able to exploit these processing cores, and you are able to get better throughput in terms of the execution time or the floating point operation per second. So that's why GPUs have become very popular now. They are there in a large number of domains, not just the earlier design of the motivation was just graphics applications like media entertainment, but nowadays they are there in large number of applications like general purpose applications like climate modeling and the computational fluid dynamics in mechanics and security, medical imaging in the medical field. And you also see in the deep learning or machine learning, you see it's very actively used. Without that, people not get good speed ups. And in education and research and supercomputers, you see that GPUs are there. So GPUs are used in large number of domains because they allow you to get a better throughput. But one problem with the GPUs currently is that so they have a very limited memory size. So you can see that over the several years, over the generations, you can see that K40 to M40 and P100 and V100, you see the memory sizes are not growing that much. So say around 16 GB, or see K40 has 12 GB, and then V100 has 16 GB, and the latest A100 architecture has around 80 GB. So you can see that GPU sizes are actually very short compared to the data that we need to process. The data is actually very huge in size with the real-time data. It can go up to thousands of gigabytes of data. So, so this is one of the limitation of the GPU. So memory sizes are very
Excuse me, sir.
yes.
So what does this memory size means here?
Yeah, GPU also has a dedicated memory. Like how CPU has a DRAM, then GPU also has a dedicated DRAM.
A better memory controller won't help in this case.
No, actually the memory capacity is less, right? So there's a lot of research is going on about how to pack more and more GPU here, because energy is also one constraint. So you have to take about all into consideration to increase the capacity.
Okay.
So why can't the GPU be connected to the CPU's RAM?
Yes, it is there with CPU itself. So within the you will have one machine, and then you will have some specific board where you have a GPU slot, and CPUs and GPUs are connected physically. The processing
Okay,
code. They are
I meant
connected
like,
using either PCI Express or some kind of any kind of bridge interface that they will have.
sir, I meant instead of having a separate memory, why can't it use the CPU's DRAM?
Yes, it can use it. So the problem is that latency is the problem. So when you try to use the entire latency, whether when you try to, because when you try to access GB memory, which is local, it will be fast. Otherwise, it's going to take some time. But the research is also progressing about how to exploit the CPU memory also. There is a concept called unified memory. So I'll talk about that in this today's talk itself. How to you
Okay,
can
sir.
exploit CPU memory to improve the memory capacity also. Okay.
Do all cores have that much dedicated memory?
No, no, no. It's a common memory that is available for all these processing cores. I've shown you right here. So all the process will share one common memory. This is called as global memory or the DRAM.
Okay, okay, sir. Okay.
Along with it, you also have a dedicated set of registers for each processing cores. That is a register file that can be shared across by all the processing cores that is there within each streaming multiprocessor. Okay, now because the memory has become one of the constraints, so people have started now going for having multiple GPUs. So just to having limit the memory capacity, just to address the memory capacity issue. So nowadays you have in one machine, you have multiple GPUs now. So this is an architecture of a DGX1 system. Nowadays we have DGX2 also. So DGX1 consists of 8 GPUs. So these GPUs are internally connected using high bandwidth interconnect called NVLink, and then GPUs and CPUs are also connected using some PCI Express switches that you can see here. So if one GPU needs to communicate the data from other GPU, then you can actually use the NVLink interconnect to transfer the data using high bandwidth. So when you have multiple GPUs, now you can accommodate more and more data, and then you can process the applications. So this is actually some of the overview about GPUs in terms of the architectures and how they have evolved. And now let me talk about some of the programming aspects. How do you write programs for GPUs? So before that, any other questions you have? I would like to take a pause over here.
Sir, are there register files specific to each code within the multi processor, or it is
And okay, each streaming multiprocessor has certain register file. Okay, let me see if I have the register file size here. Okay, so register file size it's here. Okay, I'll show you. I hope you can see. So register file size for each HM is actually 256 KB in case of K40, and it's actually same across all the 4 GPUs. So 256 KB is actually a good number. So 256 into 1024, depending on the number of processing cores, you can see that you can divide that the size into these processing cores. But any processing core can access this entire register file size.
okay.
Any other questions? Let me see if there are any questions in the chat box. Okay, thank you. Okay, then I think I can move on. Please interrupt me in case you have any questions in between. Okay, now we have understood briefly about how the GPU architecture is. Now let's see how to write some programs on the GPUs. So there are two popularly some kind of programming models that are available. One is the CUDA. This is called Compute Unified Device Architectures. This is mainly supported for NVIDIA GPUs. And this is an extension of C programming language. So if you know C programming language, it should not be very difficult to learn this extension. And this is popularly used in very academia, and this is actually because this has a good performance when you try to write programs on the NVIDIA GPUs. There is also other programming language that is supported that is called as OpenCL. This is called Open Computing Language, and this is an open source, and it supports various other GPU devices also. But if you have to write some programs on the NVIDIA GPUs, then it is preferred to use CUDA programming language because it is optimized for the NVIDIA GPUs. Let's try to understand how the GPU program actually looks like. So now you have one machine. On one machine, you have CPU cores, and you also have memory. And within the machine, you are also having a GPU. There is a slot to put the GPU, and GPU now has streaming multiprocessor. So each streaming multiprocessor, now you have several thousands of cores. As I said, you have memory, device memory or global memory, also DRAM. So GPU also has a dedicated DRAM now. So now when you write some program, so let's say you want to execute some application and you want to write that to be executed on GPU, not instead of CPU. So what you will try to do is that first you transfer the data from CPU to GPU because the data is originally on CPU. Now you transfer the data. Now the data will be on GPU. Now once the data is in there, you perform the computation on the GPU. The computation that you want to perform, that you want to parallelize, that is called as a kernel. So this is called as kernel, and that will be executed on GPU. Now the results, once you have computed, performed the kernel operation, the final results will be in the device memory or the global memory or DRAM of the GPU. Now once the data is in, but the data we need to transfer the data again back to the CPU memory. So this is how you transfer the data. So GPU to CPU transfer you do. So whatever computation you want to do, you first transfer the data and then perform the computation and then transfer the data back from the GPU to CPU. So this is how the typical operation takes place when you write CUDA program. When you write a program using CUDA language. So let's try to understand in terms of a simple example how we can write this programmatically, the systematic steps. Okay, so this is a simple example of a CUDA program. Here what we are interested is we are given an array and we are interested in actually squaring each and every element in the array. That's a simple program that you are interested in. And we want to perform that operation, that the key operation we want to perform, let's say, on the GPU. So first you write the program as the main program that you write in C language. So you write the main function. In the main function, you allocate an array with a desired size. And then this data is actually allocated now on the CPU. That is called as a host array. But we also need to transfer the data on the GPU. So for that, you also allocate the data on the GPU. That's called as the device. So there is a construct called CUDA malloc that allows you to write, that allows you to allocate memory on the GPU. So here your CUDA malloc D underscore A basically shows you are allocating some memory on the GPU. Now you have the memory allocated on CPU and then GPU. Now you initialize the data on CPU. So basically you are initializing the host array, basically the array A on the CPU. Now once you have once the data has been initialized on the CPU, now you transfer the data from the CPU to the GPU. So for that there is a system call that is provided CUDA mem cpy. So it takes certain parameters which says that HA, basically it says from host array you want to copy to device array, and you also specify some construct saying that CUDA mem cpy host to device, which you are telling that you transfer the data from the CPU to the GPU device. This is what you are specifying it. Okay, so this is the first operation we are trying to do. You allocated the data on CPU, you initialize the data on CPU, now you are actually transferring the data. So the transferring the data. Once the data has been transferred, now the data is there in now GPU. You basically transfer the, you perform the operation. The operation is actually called as square operation, square kernel. So we write a function, that function called kernel. So it is actually called square kernel. It is as good as you write any kind of function that you write, but it will be executed by all the threads that is participating in the program basically. So in each function, what you are interested to do is that you basically, let's say you have several threads. So you first compute the thread ID, and then each thread basically takes one element and then does the multiplication by itself. So let's say thread ID is performing taking the index I, and then it is performing the operation AI into AI, and then it's putting the result back again into the A itself. So now you have the data A is basically now on the GPU. After you transfer, you are doing the squaring on that AI into AI, and then the resultant array is also on the GPU memory. Now finally, once the operation has been performed, then you transfer the data from the GPU to the CPU. So the construct again you see CUDA mem CPY, the source is DA, and then destination is HA, and then you specify it as CUDA mem CPY device to host. So now the data is now finally on the CPU. You have processed, and you can do anything that you want to do with the array on the CPU by processing the data. Once the data has been processed, you can just free the memory of the GPU and then free the CPU memory as well. So this is how the simple operation you take it. So you are interested in taking an array and you want to perform the square on each and every element that is there in the array. So all the yes.
Does the programmer define the number of threads?
Yes. So here that is what the number of thread is actually specified using thread configuration. So that I will come in the next slide. So this operation, the function, is that clear to you? First of all.
Yes.
Hello?
Yes,
Okay.
sir, clear.
Yes. Okay, so now the portion of program, basically the portion is squaring you are taking each and every element and that is and squaring it. So that portion is actually called kernel, and this kernel is actually executed by as many number of threads as you specify. So you can specify, because you have so many processing cores, so you can specify the number of threads accordingly. So you can specify 1024 cores, or maybe 1000 number of 24 threads, or sometimes you can specify 16,000 threads, so on and so forth. You can specify depending on the problem size. You can specify as many number of threads. Let's say your array size is 1024. You can specify the number of threads, effective number of threads as 1024, and each thread ID basically takes one element in the array and does the multiplication and puts the result back into the same array. So you can see that. So now these threads are basically mapped down to the processing cores and they execute it independently, parallelly, and you can get the high throughput. So this is how the simple example looks like, how to do the how to write some simple program on the GPU. So depending on your complex problem, you can do the similar, you can parallelize the application on the GPU. Okay, so is there any question on the basic simple program before I move on to the how to specify threads and everything? Okay, so now, so the first step here is the CPU to GPU transfer, and then this is invoking the kernel. Basically, you have written the kernel, you are invoking it. So this is a way in which you invoke the kernel. So here you specify thread configuration. It will specify the number of threads. Basically, I will show you how you specify threads, and then after that you have the compute kernel. Then once the data has when the operation has been computed, then you transfer the data back from the GPU to CPU. Now now let's see how you specify the thread configuration. So you are actually calling the function, that's kernel function, square kernel. You're specifying the parameters here, and then you have to specify the thread configuration. So thread configuration is effectively meant for specifying how many threads you want to launch it. But GPUs allow to specify thread configuration in a slightly different manner than the traditional MPI that you OpenMP use. So here you specify the thread configuration in terms of thread blocks and the number of threads. Basically, you can say, let's say you have 32 threads you want to specify. You can specify 32 threads, saying that I want to have 8 thread blocks, and then each thread block there are 4 threads. So effectively 8 into 4, there are 32 threads you can specify. So you specify the thread blocks and you specify the number of threads within each thread block. This is how you specify.
So is a thread block the same as a warp?
No, it is not. Warp size is 32.
Always.
Warp size is always 32. Thread block size can be anything. Okay, so
So what
this
is the benefit of this?
I will show you in the next slide. Okay. Okay, so this basically this kind of organization gives you some kind of benefit in terms of scalability. Okay, so you know that I've shown in this slide that okay, so different GPUs are nowadays having different number of SMs. Okay, so now this kind of facility will now the having different kinds of thread blocks and different threads actually gives you a facility to scale by varying the number of scaling the number of SMs accordingly. Let's say that you have two GPUs. The first GPU has 4 SMs and the second GPU has 2 SMs. Okay, now with this kind of thread block mechanism, you should still be able to execute the thread blocks efficiently on the GPUs using this on this SMs. Let's try to understand it. Okay, so let's say that you wrote a program that has 8 thread blocks and there are 2 threads within each thread blocks. I hear some noise. Okay, now it's clear. So now if you have a GPU which has only 4 SMs, then you can spread the 8 thread blocks in such a way that each SM gets 2 thread blocks. So internally. Okay. Now the main thing that you have to understand is that each SM can only take the full thread block. It cannot take partial thread block. So if you had only specified one complete thread block, then it would have gone to only one of the SM and then remaining SMs would have been remain idle. Now, because you have 8 thread blocks, so you can actually specify each SM can take 2 thread blocks and then process them. Now, if suppose on the other hand, now you wrote some program, but you want to execute on a different GPU, but different GPU has fewer SMs. Let's say it has only 2 SMs. In that case, it is still possible to launch the thread blocks, but now each SM will take 4 thread blocks now instead of having 2 thread blocks. So each thread block can go up to 4 thread blocks, and now this each thread block is again sorry, each SM has 4 thread blocks, and each thread block again has 2 thread blocks. So this is how you can split evenly across the multiple SMs depending on the number of SMs available. So if you had only one thread block and you had specified all the threads within that, then maybe only one of the SM could have occupied it, and the remaining SMs would have been be free idle. So you're not actually exploiting all the processing cores. So this gives you some kind of flexibility in terms of locking the number of thread blocks onto the SMs, onto the GPUs and SMs, etc. I hope that's clear to you now. Now let's try to understand how the instructions get executed on the GPU. Okay, so this is about how the thread blocks you specify, how they get mapped onto GPUs. But now let's try to understand how the instructions get executed. Now let's try to understand how the execution takes place in each SM, and the similar execution will go on in one SM, and then we can understand the similar execution will go on each SM. Okay, let's consider this scenario where one SM you have 4 thread blocks. Okay, so let's say you have 4 thread blocks. Each SM has. Now let's say the block size is, for the sake of simplicity, you can assume that 128 threads, and the number of blocks is, let's say, 4 you have. Okay, so effectively you have launched 512 threads in each thread, in each SM basically. Now internally, what happens in the GPU is that GPU tries to group this 512 threads into what is known as warps, and the size of each warp is 32 threads. So the moment that thread blocks are launched, they are grouped into warps, and each warp is 32 threads. Now effectively this thread blocks configuration is basically translated into this fashion. So each block now has 128 threads. This corresponds to 4 warps. This is basically 4 into 32 threads. This is 128 threads. So first block has warp 0, warp 1, warp 2, warp 3, etc. And the second block has warp 4 to 7, and so on and so forth. Now these warps, let's see how actually instructions get executed. Now you have 128, let's say here you have 16 warps that are launched in one SM, let's say SM0. Now the programmer has written a program, and you have several instructions. So now what happens is that there is something called as a warp scheduler in the GPU. So each warp basically takes one instruction at a time and executes the same instruction on multiple data elements, and then gives you the output. So the warp 0 is basically consisting of 16 threads. So all the 16 threads bring the first instruction. Basically for warp 0 is basically the instruction 0 that it has to execute the first instruction, and then it executes. So all the 16 basically all the 32 threads basically execute the same instruction, instruction 0, but they execute the data, perform the operation on different data elements, but the same operations. Instruction is same, but the data could be different. Now these 32 threads are actually mapped to the 32 processing cores that are available, and then you can see that in one, depending on the operation that you are performing, let's say if it is add operation, then you can, depending on the latency, you can see that in 1 unit of latency, you can actually get the 32 operations done in one single cycle itself. So like now let's say warp 0 has finished actually execution. Now you can take another warp, let's say warp 1, let's say if it is available, then you can execute its first instruction. Its first instruction is again instruction 0, because all threads have to perform the same operation. So all the 32 threads again in warp 1 will execute the same instruction. So on and so forth, you try to execute all the warps, the first instruction. So all the basically warps have to execute the entire program. So each warp actually executes its first instruction, and after that, now again you can execute the warp 0, but the second instruction, whatever it has it, and so on and so forth. You can execute until all the program instructions are actually completed. So this warp scheduler is actually we have taken, it's actually a round robin scheduler. So here you take the first warp 0 and then warp 1, warp 2, and so on and so forth. But you could also have a different warp scheduler that GPUs can implement it. So depending on the warp scheduler, you can issue the you can actually fetch the instructions and then issue the warps for the executions. So this is how actually the instructions get issued by the warps and try to execute it. Now let's also try to understand a little more about how actually warp executes each instruction. Okay, let's try to understand how warp 0 executes one instruction. Let's see. Okay, so now let's come back to the same program where we have written CUDA program and see one of the instruction. Let's say how the instruction gets executed. The main operation here we are doing is the multiplication. You are performing an element. Each thread is actually taking an element and doing the multiplication with itself. So this is the key operation that we are trying to do. Let's actually see how the GPUs will execute how the warps get executed these instructions. Now let's say you have warp 0 that is trying to perform the multiplication operation, and in the warp 0, let's say you have the 32 threads. The 32 threads are numbered from T0, T1, T3, etc. up to T31. Now each thread will take one data element because you have written it as AI into AI. I is based on the thread ID. So T0 will process A0, and then T1 will process A1, so on and so forth. T31 will process A31. So now you have a warp which needs to execute the same operation. Operation is same multiplication, but you are performing on different data elements. Now you have several thousands of processing cores. So you have these, actually the computations are actually mapped onto the 32 processing cores, and each thread basically gets mapped onto one processing core and does the multiplication in parallel, and all of them do at the same time, and you get the operation done in one unit of time, depending on how much time you take for the multiplication. So in that multiplication latency, you are going to say that all the 32 computations are going to be done in 1 unit of latency cycle that is required for multiplication. So T0 does the multiplication A0 and A0, T1 does the multiplication in A1 and A1, and T31 does the multiplication on A31 and A31, so on and so forth. You can see that you can get the performance, you can get a very high throughput by exploiting all the multiple processing cores that are there in the GPUs. So now let's try to understand how actually thread blocks you can specify for this particular program. So depending on the problem size, the user actually can specify the thread blocks according to whatever his desired configuration. So the CUDA programming allows the programmers to select the thread block size. Let's say if the thread block size is 32, the problem size is 32,768. Let's say if your array size is the array that you're performing is about 32,768, then you can specify the 32 thread blocks, or maybe you can specify 1024 threads, which is each thread block, or you could also specify 128 thread blocks, and then you can specify 256 threads. So each thread will perform, take one element of the array and then does the multiplications. So on and so forth. But there are also some constraints on how many operations you can specify, how many thread blocks you can specify, and what is the maximum thread block also you can specify. And if you want to specify what is the best thread block occupancy that you can get, there is to specify, there is a tool called CUDA occupancy calculator that's available online, that tells you what is the desired configuration that you can select for having the better occupancy or better resources utilizations. And as I said, you cannot arbitrarily specify the number of threads and thread block sizes. There is also a limit on how many thread blocks, how many threads you can specify in each thread block. So that you can get it using some specifications of the GPU specification. If you see here, so your max thread block size. Okay, so this is the data size, you can data sheet you can get from the NVIDIA. So the max thread block size is 1024 for various GPUs, you can see. So you cannot have the thread block size which is more than 1024, but you can have arbitrary number of thread blocks. So that cap is there, so that you have to look at to the specification when you write programs. But there is no limit on the number of thread blocks, but you can specify the thread block size, that is the limit. Yes, please go ahead.
So the only reason we are splitting it into thread blocks is to assign it to different SMs.
Yes, yes.
And
If you had only specified,
after it goes to each SM, it splits into warps.
yes. Yes, yes.
Sir, I have a doubt.
Mm-hmm.
So, how do we understand like what kind of threat can be given? Like, is there any limitation or?
I said that first you choose your problem size. If the problem size is very depending on the problem size, basically you split the number of thread blocks and the number of threads within each thread block. However, keep in mind that the number of the thread block size of each thread block can be maximum 1024 maximum. So let's
like
say
what if we have some very
yes, the number of thread blocks can be varied, right? It can be very high number, but the thread block, the size of each thread blocks can be, you can have a maximum limit. So for example, I'm telling you, so the size of the problem you are handling 32,768. So you can specify as 32 thread blocks and 1024 thread, but you cannot specify as 16 threads and 2048 threads in each thread block, because the maximum limit is 1024 only. But you can have maximum, you can have arbitrary number of thread blocks. There is no limit on that.
Like, I'm not able to understand like why the number of threads is being a criterion, not the size of total threads for each block.
Okay, so now let me explain with some example. Okay, so when you write some program, you specify number of thread blocks. Okay, so let's take this program. Okay, so now you can see that for now you specify, let's say 1024 threads. Okay, so the entire program is executed by this all the threads. Now when this program gets decoded by the compiler, then this basically transfers to some kind of assembly program, right? In the assembly program you have registers also, right? The operations requires to use registers. Now for each thread, let's say if when you try to decode this kernel, you translate this kernel into assembly code. Let's say this program requires around 20 registers. Then each thread is given 20 registers separately. So then you say around 1024 threads you are launching. Then each of the thread is actually going to get 20 registers. So 20 into 1024 registers are going to be allocated. But there is also a limit on how much register sizes that are there in each SM. I have shown you. Okay. So here the register file size is also limited. You cannot go beyond whatever number. So if you increase, let's say beyond 1024, then you will not be able to accommodate basically the registers corresponding to it. Also, there is also shared memory corresponding to in each system. You will not be able to accommodate it. That's why they don't allow arbitrary number of thread block size.
Yes, sir. Understood, sir.
Any other questions before I could move on to some of the optimizations?
So last question, is there any relationship between the number of threads and the number of cores in a streaming processor?
No, actually, it is not there. So let me tell you that your problem size is, let's say, 1 million. Okay, but
Okay.
the processing cores can be there is a limit, right? Depends on the GPU specification. So maybe in V100 you have 5,000 cores or so. Okay, so but your problem size can be 1 million. So first you can specify as big as 1 million threads total by specifying the number of thread blocks and threads configuration. So first a few threads will be lost depending on how many resources are available. Once once the operation on those processing cores are finished, the next set of threads will be launched, so on and so forth.
Okay.
Okay.
So the programmer usually doesn't have to worry about the
Worry
relationship.
about, yes, he
Okay.
doesn't have to worry. He just specify the size, number of thread block size, thread blocks, and number of thread blocks, and then executes its applications. And then now internally the GPU will execute accordingly, depending on the resources available.
Okay.
Okay. I can wait for about half a more minute to see if there are any other questions.
Sir, just correct me if I'm wrong. So basically, we receive the threads, we schedule them into warps, and then the warps, the compiler automatically decides what are the SMs to be optimized with respect to a warp, right?
Yes, yes. In the warps also you don't decide. It is the GPU decides. The grouping is also done by the GPU. That it's a hardware, and the execution also is decided by the GPU. The how to allocate the which thread will go to which thread block will go to which SM. That is also decided by the GPU hardware. The programmer does not have the control. All the programmer does is basically specify the how to do the problem, how to solve the problem, and how many thread blocks you want to specify. All the mapping will be taken care of by the GPU.
Okay, sir. Thank you.
Okay, so I have just explained how the instruction goes so that you also understand in terms of architecture a little bit more about how the execution goes on, how it is different from the traditional the CPU architecture that you see or the multi-core CPUs that you see. Okay, so I think we can go to the next subtopic, that is about how to optimize the programs. What are the different kinds of optimization that are there on the GPUs? Okay, so now you have understood about how to write simple programs on GPUs using CUDA programming. So CPU you transfer the data and perform the computation, and then transfer the data back from the GPU to CPU. Okay, now there are several optimizations can be performed. So one optimizations can be performed. There are several optimizations on how to minimize the data transfer, CPU to GPU or GPU to CPU data transfers, because the research has shown that there is a significant amount of time is spent in transferring the data from CPU to GPU or GPU to CPU data transfer. And there are also a lot of optimizations that you can perform at the kernel level. How you can write actually better kernel, better computation, so that GPUs are very full utilized. The GPU processing cores are very well utilized. So these are the two different directions of research people are trying to do it. So in the interest of time, I'll talk about some of the optimizations only related to the data transfers, but there are also optimizations at the kernel level. Okay, so the study shows that CPU to GPU data transfer consumes significant of time. So here we'll talk about briefly about how to reduce the data transfer time using called as pinned memory, and also I'll talk about how to minimize the data transfer time by overlapping the data transfer with the computations on the GPU. And I'll also talk about how the unified memory, the latest the technology that is there, how you can exploit the CPU memory to improve the address the memory utilization, also data transfers, etc. These are all related to the data transfers. Of course, as I said, there are optimizations at the kernel level, like global memory or access coalescing. How do you address the shared memory effective manner? How the L1 cache, L2 cache, how the schedulers come into picture. So all that are there respect to the GPU kernel itself. So all that are there, that's different topics. But here we'll talk about CPU, how to optimize the data transfers. So the first one is actually how to optimize the data transfers using the pinned memory. Okay, so let's try to understand maybe with a simple example. Let's say you have a simple program in which you are allocating the data on CPU, and then you are allocating the data on GPU, and then you are initializing the data, and then you're copying the data from CPU to GPU, and then you are performing the computation on GPU. So this is simple CUDA programming, and this is some simple pseudocode corresponding to it. Okay, now let's see how actually what happens when you transfer the data. Okay, so GPU has a dedicated memory, that is a device memory or DRAM or global memory, and now CPU also has a memory, that is a DRAM memory. Okay, so by default actually whatever you allocate the data, that goes into memory which is pageable. So you know that paging, you know, in operating system you have the concept of paging. So the data that you allocate, it goes to the pageable memory, which means that depending on the OS page replacement allocation algorithm, the page can be getting replaced on the CPU. Okay, so now let's see how the data transfer takes place from CPU to GPU. So you have to move the data from CPU to GPU. So before that, what actually the controller does is that it transfers the data from pageable memory to the pinned memory. So the pinned memory is nothing but the data is actually cannot be replaced. So just to make sure that the data while copying it won't get replaced. So the CPU engine basically transfer the data from pageable memory to first pinned memory. Once the data is in pinned memory, it cannot be swapped. It cannot be swapped by any other page replacement algorithm. And then once the data is in pinned memory, then it actually transfer the data from pinned memory to the device memory. So this is how the data transfer takes place. When you write CUDA mem CPY, this is how the data transfer will take place. So now you can see that clearly there is some amount of redundant data transfer. Now there is first data transfer from pageable to pinned, and then from pinned to device memory. So this optimization, so one optimization to improve the data transfer is basically exploit the pinned memory. So the CUDA programming language actually supports, there is a construct called CUDA malloc host. So what does it say? That instead of allocating the data directly on the pageable memory, you directly allocate the data on the pinned memory. So now when the data is pinned memory, when you do the data transfer directly, the data will be transferred from CPU to GPU, and there is no redundant data transfers. So maybe you will be asking that it's good that now pinned memory is good is optimizing the data transfer. Then why can't you allocate everything on the CPU pinned memory itself? But the problem is there is a limit on the pin memory size, and if you allocate too much data on the pin memory, the CPU performance can go down because you have very limited pageable memory. In that case, then the OS might actually suffer a lot. So you should have a good balance on the pin memory as well as pageable memory. How do you allocate it? So this is one optimization. Now the other optimization is to overlap the data transfers using the strings, the concept of strings. So maybe let's just briefly try to wrap up. Okay, so this is a simple program, you try to do it. So CUDA mem CPY you write, you transfer the data, and then you perform, let's say, some computation on GPU, and then you transfer the data from GPU to CPU. Okay, so typically the data transfers are blocking calls. So blocking calls means, so you cannot CUDA mem CPY unless and until it is finished, you cannot go for the next instruction, that is increment operation. Similarly, this also, the CUDA mem CPY is a block operation. So unless until the data transfer is finished, you cannot actually execute the next instruction. But the kernel execution is asynchronous. Asynchronous means once the kernel has actually been launched, that the control will directly transfer comes over here. So the thing is that one optimization that you can try to do is that, so since the kernel launch is asynchronous means it doesn't wait for the data to the kernel computation to finish, the control can directly transfer some here. Control actually transfers here. Okay, so in between the kernel computation and then the data transfer, there is some amount of time. Okay, so the CPU is actually remaining idle. So now to improve the CPU performance and also overlap computations, you can do some arbitrary computation on CPU, so that CPU is also very well utilized. So I think we are running out of time. So maybe in the interest of time, I'll skip this particular optimization and I'll talk about one of the unified memory technology that some of you had doubts. Okay, so some problem that people were suggesting that, okay, so GPUs have limited memory, then how can we actually try to, can we try to use the CPU memory to assess the memory limitations? So the answer is basically unified memory. So this is the latest technology that is provided by the basically NVIDIA GPUs that says that basically optimizes that utilizes the GPU memory as well as the CPU memory, and the programmer doesn't have to worry about where you're actually allocating the data, and the data transfers are automatic. So without unified memory, let's see how the programmer writes the program, and with unified memory, how the programmer writes the program. So this is without unified memory. Basically, you do the data transfer. You initialize the data on CPU as well as GPU, and then do the data transfer and on the computation, and then again transfer the data from GPU to CPU. This is how you try to do it without a unified memory. Now, if you have the unified memory, the programmer does not specify does not specify the allocation policy. It's just specify that you allocate the data. So the data can be allocated or the GPU or the CPU. It's decided by the system. So you can specify a concept called CUDA malloc manage, and then you execute the kernel operation, and then you process the data once the data has been when a computation has been done on the GPU. So here you don't specify the explicit data transfers. The data is allocated and the transferred by the GPU automatically either CPU on the CPU or GPU, depending. If suppose you are accessing the data from GPU, the data will be transferred automatically from the GPU to CPU, CPU to GPU, and then if you are accessing the data on CPU, then it will be transferred from GPU to CPU, so on and so forth. Let's try to understand how unified memory works internally. Let's say you have CPU memory and then you have GPU memory. When you specify CUDA malloc managed, then initially the pages may not be allocated anywhere on the. It may not be allocated on CPU or GPU memory. Now let's say you are accessing a page on the CPU for the particular array. Then the CPU actually issues a page fault. Then the page will be loaded onto CPU. Now let's say after some time you are accessing the data on the CPU itself, and then the page faults will be raised, and the page faults, let's say they are addressed. Let's say you have started the GPU operation, the kernel computation. Let's say you are accessing the data. Now the data is not in the GPU. Internally the system transfer the data from CPU to GPU, and so on and so forth. Let's say you are again accessing a page that is not in the GPU. Then again the data transfer takes place, and then you keep on loading the data. So if let's say if you are accessing again a data that is in CPU, the data will be transferred from GPU to CPU, etc. So the data transfers are automatic. Programmer doesn't have to specify. Now you could use the full GPU memory plus CPU memory to address the memory limitations. So unified memory supports processing on large inputs. So pages may not be allocated on GPUs upon CUDA malloc manage, and page faults can occur on both CPU as well as CPU. And oversubscription of pages is available by evicting the pages on GPU. When you say oversubscription, which means that you can also access the data that doesn't fit into the capacity of GPU memory. So if the data is doesn't fit into GPU but it can fit into CPU, still you can access the data using this unified memory technology. So a quick summary: optimizations are critical for performance. Programmers have to be understand about some of the architecture features. Also, the architectures are also working on serious research directions to improve the performance to improve the performance of GPU architecture. So basically, we talked about some of the data transfer, but there are a lot of optimizations at the kernel level, like warp divergent, access pattern, resource utilization, that can be done at the kernel level. So now I think we have come to end of one subtopic, and before I could move on to some of the research directions, let me see if anybody has any questions. I can wait for about half a minute or so, half a minute to 1 minute. Let me see in the chat box
I
also.
have a small question, sir. So, what does CUDA device synchronize?
Yeah, so basically it waits for the device operation to finish. So here, right? Basically it waits for the kernel operation to finish. So let's say if you did not write and then you are trying to start the accessing the element A, the accessing the array in the CPU. So this is a asynchronous call, which means that as soon as you launch the kernel, the control will come back and start executing the next operation, right? Process A. But there is some kind of dependence. Maybe that you want to process the operation on the GPU, and then once the data is been finished, then only when the computation is finished, then only you want to access. But since it is asynchronous, it start accessing the data. You don't want that. You want the operation to finish. So that's why you write CUDA device synchronous.
Oh, the previous one, like CUDA memcpy, was blocking
Blocking it. Yes, it was
where
blocking
we
it.
needed this. Okay, sir.
Yes, yes. Let me see. Okay. Okay, so then I have a couple of slides on some of the research directions, how the GPU research has been going on in terms of programming and architecture, etc. Okay, so some of the challenges in the GPUs nowadays is actually the data growth. So the data has been increasing exponentially. Let's take simple example of graph analytics. So the real world graphs are very large in size. It can go up to terabytes of data, but GPUs has very limited memory. For example, NVIDIA P100 has 16 GB memory, and now the latest A100 architecture also has very limited memory up to 80 GB only. So how do you actually process this very large graphs onto this GPU memory? That is one actually the data concern. Data size is actually one concern, and the other concern is about the energy efficiency. So you can see that GPUs nowadays you have thousands of processing cores, and the leakage energy is actually increasing exponentially. So if you see this graph, you can see that there are multiple things it shows. The blue color line basically shows the gate length of a transistor. It shows that it has been decreasing. Because gate length has been decreasing, you are able to put more and more chips onto the more and more transistors onto a chip, and that's why you're able to improve the performance. But the problem is when you're putting more and more transistors, the power has been leakage power has been increasing, and it has been increasing exponentially. So this is called subthreshold leakage, is one of the components that is responsible for the leakage energy. So there is too much amount of leakage energy, actually leakage power has been increasing. That has become a very serious concern for the GPUs as well, not only for CPU. So architectures, people are trying to look about how do you optimize the power and energy efficiency so that you can get better performance without having the increasing the energy. So this is one kind of challenge. And the other thing is that, so now because the data size is getting limited, so people have started looking into multiple GPUs. So people have started into multiple GPUs that are located on one machine, or you could also have distributed GPUs, like various you can have machines. On each machine you could have GPUs, and they are connected using some interconnect. Then how do you process, how do you improve the performance of these applications when you have multiple machines and multiple GPUs within each machine? So how do you partition the problems effectively, and how do you synchronize the processors, and how do you compute, how do you perform the computation effectively on each GPU? So this is one kind of challenge. So the research has been going in several directions in the whole system stack. Like in the architecture, people are trying to do it. Also in the compilers, people are trying to do it, and also people are trying to research about how to have better runtimes, and also how to develop applications efficiently. So a lot of research is going on in several directions. The goal is to improve performance and also resource utilization and energy efficiency as well as programmability. So these are the some of the key research directions. Let's try to go into each of these tag, and let's see what kind of research is going on. So the first one is architecture. So the goal of architectural research is basically come up with a better architecture so that you address the to improve the performance and address resource utilization and energy efficiency. So let's just give a brief overview of how things are working on the architectural research. So you have in the GPU architecture, you have set of streaming multiprocessors. As I said, you have within each streaming multiprocessor, you have registers, cache, shared memory, and L1 cache, and you also have schedulers. You have L2 cache and global memory. So there is large body of research that is working on exploiting each of these resource units. So some research is going on research registers, and some research is going on scratchpad memory, and some research is going about how to improve the cache memory access pattern, how to address the cache latency, so on and so forth. So large body of research is going in terms of architectures so that you can address the performance and energy efficiency, etc. Okay, now to address the memory limitations also, people are trying to, there is a large body of architecture research is going about to address the memory limitations also. One technology is unified memory that GPUs have proposed, NVIDIA. So basically, how do you exploit the CPU memory as well as GPU memory effectively so that you can address the GPU memory limitations also. And there are other research directions also. For example, so people have started coming up with CPU and GPU heterogeneous architectures also. So whether when you can have where CPUs you have GPUs, when you put them together, how do you exploit the performance of the application so that you exploit GPUs as well as CPUs, because CPUs have their own advantages and GPUs also have their own advantages. So when an application actually requires both CPU and GPUs in a different way, then how you can partition the problem across CPU and GPU, that is also one set of research direction. And these days, people have started using machine learning for GPU. So how to develop effective machine learning frameworks and programming runtimes that can exploit GPUs, that is also one research. And how you can solve and there are also machine learning techniques people are trying to use for in terms of GPU architecture itself. How can you leverage machine learning techniques to improve the GPU architecture itself? That is also some kind of research is going on. And the other kind of research is on high performance distributed GPU computing. Now you have several GPUs that are located on several machines. Now how do you address the partitioning, computation, effective communication, etc.? So there is also large body of research how to do the performance distributed GPU computing, and for how do you come up with the different simulators or GPU simulators so that you can also in terms of architecture community, how can we improve the performance? So these are there is also research in developing effective simulators or improving the architecture of GPU simulators also. So to just to summarize my talk, so GPUs are becoming very popular platform for developing applications. They're used in very domains, large number of domains. And so this talk is mainly to give some introduction to GPUs in terms of architecture, how to write some simple programs on CUDA programming, and I talk about some of the optimizations and try to give some of the research directions. GPUs, even though they are popular platforms, so there are some limitations in terms of memory and high performance computing, and so energy efficiency. So there is a large body of research is going on to improve the performance, energy efficiency, and resource utilization, also in terms of distributed systems. So I'm happy to take a questions right now and pause for a few minutes.
So can you elaborate why each ISM has so many processors?
Okay.
That's useful.
Okay, you want to know why they are able to put it, right? So earlier in multi-core processors, let me show you. Okay, each processing core now you have instruction fetch. Okay, you have a decode unit. I mean, for each processing core, you have a dedicated set of ALUs and everything, right? Here and now you can see that in GPUs the scenario is slightly different. Okay, let me show you here. So each warp is actually executing very common instructions. Okay, so each warp is now 32 threads, right? So 32 threads, now you don't need 32 instruction fetching units. So one instruction is being fetched for all the 32 units. Now you can pack everything into one itself. Now instead of having 32 program counters and 32 instruction buffers and 32 decode units. Now you can have only one unit, right? So you are able to put, you are able to actually compact lot of units into one unit itself. Did you get it? Suppose if you had to execute, each thread has to execute different instruction, then you need different program counter, different register unit, and different instruction buffer, etc. Now you are putting everything into one, you are compacting into one unit itself. So that's why you are able to put now more and more execution units instead of putting all these memory buffers or anything like that. Is that the intuition clear to you?
So more threads basically.
More threads you are able to require, you are able to accommodate with the fewer buffers also.
Yes, sir.
Okay. So I didn't get time to, I think I would have covered this streams, but I think it will take some more time. So maybe I'll stop. I will not take that. Okay.
Hello, sir.
Yes.
Sir, in case of unified memory, you talked about in case of page fault, the memory is transferred, the data is transferred from the host device to the host memory to the device memory. But how is it in the opposite case when we want to, when after the computation, we have to copy the data back to the host memory?
Okay. So internally, when you try to use a unified memory, the data transfers are automatic. Let's say you have performed the computation on GPU, and the GPU is trying to do the data. Okay. So performs access some array element, and let's say after computation of kernel, now the same array element wants to be used by the CPU. Then the system internally transfer the data from GPU to CPU. The moment you need to request the data on CPU, the data will be transferred by the system. You don't do the accelerated data transfers.
Okay, so when we are processing the data on the CPU, when the page fault occur, it will check in the device memory.
Yes.
Okay, got it. Thank you.
Okay. So I may not be available for today's doubt clearing session, and just to mention that we also have a lab session today. I think it is from 2:30 to 4 o'clock. So I request all of you to just please note down if you have any other questions. I will be there to answer your questions also. So the lab session will be mainly on how to write some simple programs on the GPU. So and we'll have the CUDA, Google Colab platform where you can set up your GPUs and how to write some simple programs using CUDA programming. I'll provide all the reference materials to you there itself, so you don't have to worry about. So you'll perform some simple computations on GPUs and how you vary the number of threads, how the performance gets affected. So just try to play around with some simple programs during the lab session. Okay, I think I can wait. Okay, so there is someone okay, the copy to. So I think in unified memory, how's the data copied from device to host memory? So this is clear. Now there is one more question: is only the fine-grained parallelism be supported GPU with respect to? Okay, so fine. I mean, see, as I said, okay. So let me just, if I understand you correctly. So let's say now you have warp 0 is basically is executing some instruction. The instruction gets mapped to the 32 processing cores that are there in the GPU. Now it is also possible that there could be another warp now. Let's say while warp 0 is executing the instruction, let's say warp 1 is also ready afterwards when you are trying to issue. That warp 1 can also be executed on different processing cores. So because you have thousands of processing cores, so the first set of 32 processing cores may be processing instruction 0 for the warp 0, and the other 32 processing cores can be executing warp 1 of the instruction 0. So those two instructions can be at the different level, different stages in the execution. So so some amount of heterogeneity is also there. So all the instructions, all the processing cores execute the same instructions for these 32 threads, but they could be executing different instructions for a different warp. So it could be slightly different also. Now, when you say is only fine-grained parallelism, I didn't understand this question very carefully. If what is his name? Strail? There is one question in the chat box. Can you try to speak out? Hello? There is one question on fine grain. I'll get back in the afternoon. Okay, okay. No problem. You can come back in the afternoon. We can discuss in more detail. Okay, okay. That's fine. No problem. Okay, then I think we are done with our session. We can start the next session. Hello, hi, Madhura, are you there?
Oh, hi. Yeah, Vishwesh. Thank you.
Okay.
I'm
So I'll
here.
stop sharing the screen then.
Mhm.